Over the years, the search for the perfect sound in the living rooms of Britain has caused endless boasts about who has the best woofers, tweeters, and crossovers. Well, today a new product appears in the shops, this is it, to herald a new era of hi-fi snobbery. It's called the compact disc, which the manufacturers claim will mean the death of the gramophone record.
When you listen to a compact disc, it's immediately obvious that the quality of sound produced is far superior to that of earlier recording media. Now, it might be thought that this is entirely due to the use of advanced technology, particularly the use of a laser to scan the disc. But there's far more to it than that. And the secret lies within the compact disc itself.
Each CD has a spiral track, just like a gramophone record. But that's where the similarity ends. To start with, the track is scanned outwards from the center, rather than inwards. It's also scanned at a constant speed, just over a meter a second, so that the disc slows down as it plays from 8 revolutions per second to less than 4. And finally, and perhaps most importantly, the sound is recorded on the disc in a digital format. Any sound, whether music or speech, can be represented as a waveform like this, an analog signal. With stereo, there are 2 such waveforms for the left and right channels. To convert each analog signal into digital form, it's sampled at regular intervals, and the value is measured. The value is represented as a binary number, a string of 16 bits. The bits are processed 8 at a time. Each group is called an information symbol, and the symbols are encoded before they're recorded onto the compact disc. This combination of laser scanning and digital recording was developed in the Netherlands by Philips in the early 1980s.
Here in the Philips Research Labs, this large-scale model of a compact disc is meant just as a showpiece, but it will serve to demonstrate some of the key features of the system. This light is reflected off the undersurface of the disc as it rotates. And as you can see here, sometimes it's bright, sometimes it's dark. But it is in fact in the timing of the transition from light to dark and from dark back to light that we find the coded information.
Along the spiral track, there's a succession of pits, depressions in the surface of the disc. By contrast, the parts of the track level with the surface are called lands. The pits are of different lengths, but they're all of the same depth, just less than a quarter of a wavelength of the laser light. So the light reflected back from the bottom of a pit travels about half a wavelength further, and so it's nearly 180 degrees out of phase with the light from the surface. Destructive interference thus makes the pits look darker than the lands. Each land to pit, or pit to land transition, corresponds to a 1 bit, with 0 bits in between at regular intervals. To make these recordings, the first stage involves a master disc. This is created using a high-power argon laser. The beam is carefully focused onto the blank disc and modulated with the digital signal. Once the master disc is completed, the process of creating submasters and final production discs is then purely mechanical. There's a lot of technology involved in reading a disc too. A laser spot on the surface of the disc has a diameter of about 1 micron. This has to follow the spiral track accurately, even if the turntable is slightly off-center. Ston Bochen from the Philips Research Labs shows us how this could be done.
To show that this is possible, look at this experiment. This uses a servo system with 3 spots, 1 central spot that reads the information, and 2 satellite spots on either side of the track. If you move the disk such that the central spot goes off track due to an eccentricity, for instance, one of the satellite spots sees less of the track, while the other one sees more of the track. This imbalance in reflected light then causes the servo system to correct the position of the central spot that reads the information. Now you can clearly see that the central spot moves with respect to the position of the track.
In this demonstration, the servo system controls a mirror which deflects the spot from side to side, so that it can follow horizontal variations in the track position. But there's also vertical motion to worry about, up to 1 millimeter. This also needs to be followed.
With the help of this experiment, we can show to you how the optimal distance between the lens and the disc is maintained. It's the focus servo. The light is first focused onto the disc, and on its return path it goes through the prism and then is focused onto 2 small spots on these detectors. By the positions of those 2 spots, we can detect the optimal distance between the lens and the disc in the following manner. If the distance between the lens and the disc changes, those 2 spots on the diodes move inward or outward depending on the distance between the lens and the disc. Then the servo system responds by moving the lens back to the optimal position with respect to the disc. As you can see, the lens is mounted onto a coil which moves in a permanent magnet, just like a loudspeaker system. By making use of the error signals, as have been shown before in the experiment, we can optimally control the distance of the lens with respect to the disc.
So sophisticated control systems make sure the laser spot follows the track as closely as possible. But so far, there's nothing to suggest any improvement in the quality of the recorded signal. And this turns out to be essential for the success of the system.
The CD system would be infeasible without an efficient error correction system, since cheap mass replication of gigabits of information is impossible without creating any error. Already a new freshly pressed disk may contain hundreds of thousands of errors, and due to handling, this number of errors may increase even more. For instance, a disk full of fingerprints might sound like this if you had no error correction at all.
When Philips sought advice about the error correction built into the design of the compact disc, they found it very close to their headquarters in Eindhoven. Working here at the university is a world expert on coding theory, Professor Jack van Linde.
Let me tell you about the origin of coding theory back in the late 40s at Bell Laboratories in the United States. Richard Hamming became very irritated by the fact that his computer was able to detect if an error occurred and then switched off. And every morning when he came to the laboratories, he found that the computer had switched off. And he said, if the computer can detect an error, it should be able to correct an error. And thus he discovered what is known as the Hamming code.
So, with digital representation of sound, error correction can be used to improve quality. In the CD recording process, the signal is first converted into digital form. Then it's passed through an error correction encoder, and finally it's sent to a special modulation encoder which balances the number of ones and zeros recorded on the disc. The reverse happens when the disc is played back. The signal passes first through a modulation decoder, then it goes to an error correction decoder, and finally it's converted back to analog form to be sent to the amplifiers and loudspeakers. But how does error correction work?